Hello, friends. I'm very happy to be here and to talk about software debloating. This work is a collaboration between Stony Brook University and Boston University, and the credit of this work goes to my co-author, Rasoul, who unfortunately couldn't be here, so I'll try my best to do justice to this work. The title of our work is Minimalist, and we're doing semi-automated debloating of PHP applications through static analysis. So to start, first, we have to define what we mean by code bloat, and with that, we are referring to the sum of all unused pieces of code in an application. This can be a list of features that you don't need, or this can refer to third-party dependencies and other code that you pull into your application via libraries that, for whatever reason, you don't need them. So then we need to discuss why this is bad, and then finally show you what we can do about it. So let's motivate this by looking at this export functionality of phpMyAdmin web application, which is a database administration tool for MySQL databases. And it allows you to export your database and tables into different file formats, most commonly SQL or CSV and JSON. But there's also some obscure features here. For example, apparently some people want to export their databases to LaTeX. We're not here to judge them. But the point here is that if we can identify these unused or unneeded file formats and disable them, then we can protect the application. And we can prove this by looking at CVE details, which is a public source of vulnerabilities. And apparently, there has been 18 vulnerabilities reported for this specific export functionality within phpMyAdmin. And if we can disable and remove the code for some of these unused features, then we can prevent the exploitation of some of these CVEs as well. So we went ahead and did that in 2019 in the paper titled Less is More, which was presented in USENIX. In that paper, we created a simulated list of tests that were simulating the user's behavior to interact with the applications. And at the same time, we were running a dynamic instrumentation on the web server, collecting the list of files and functions and lines of code that would be executed. And knowing which parts of the application were used, we went ahead and debloated removed the unused portions of the code. And the results were fantastic. We could produce applications that were on average 47% smaller in terms of lines of code and were vulnerable to 60% fewer CVEs. Now, while that looked perfect, in reality, dynamic instrumentation does not scale. So during our tests, we could show that it could be miserably slow. It could increase your page load time from 2 times to 17 times slower, and that's not realistic in a production environment. And the other detail here is that if you use dynamic instrumentation, you're strictly tying your analysis to one deployed instance of the application. If you deploy the same application somewhere else with different users and different behavior, you have to do this whole analysis again. And moreover, if your application changes on the server side, meaning the state of the database is different, again, your analysis may not be correct for this new state of the database. So in order to fix that, we defined some requirements. So we wanted to have an analysis that does not have an instrumentation overhead and is also reusable. So in this work, Minimalist, and also in the next presentation, Animate Dead, our goal was to address this. And specifically for Minimalist, we performed static reachability analysis based on the web server logs. And I'm going to tell you more about that. So here, we're looking at the overall workflow of Minimalist. We have 2 main inputs to our analysis: the original web application, which is essentially the source code of our PHP applications, as well as the web server access logs. And these can be historic logs that you can collect from your web server and tell you which endpoints and which pages in the application the users requested. Then from there, we parse the source code to get the abstract syntax tree, and our ultimate goal here is to generate the call graph for our applications. So we start by looking at the source code, following the function calls, generating the call graphs, and once we have that graph, we then take into account our server access logs. Then we mark which entry points are used and which ones aren't, and then we can go ahead and prune the parts of this graph that were never used. And that's essentially our debloating. But as it turns out, now focusing on the call graph generation, it is not that simple to generate a call graph, especially for PHP applications. And some of the challenges that we faced are variable script inclusions, where in PHP you can use a variable to determine which specific PHP file needs to be included. Similarly, you can use the value of a variable to determine which target function needs to be called. And finally, we also had to have a static analysis that understands object-oriented programming to follow the functions or methods that are defined in parent classes. So to look closer at these issues, on the first line, we define a constant variable pointing to the current directory, and then through multiple string concatenations, we build a path to a local PHP file, which we then include. And similarly, we can define a variable named type and use that as the class name to instantiate a new class, or similarly define a method and use the variable as the target function. And lastly, for the object-oriented case, we can have a child class that extends a parent class. The function in this case is defined in the parent, but we're using a dynamic function call in the child to call this arrow cprint in this case to refer to the parent class. So in order to be able to generate a call graph with all these challenges, we had to do 3 types of analysis. So first of all, we had to do class hierarchy analysis, where in this analysis we analyze the inheritance relationship between classes. We then do script inclusion analysis, which if you notice in the graph, that also has an arrow input from variable analysis, where we generate the script dependency and know which script can potentially include other ones. And lastly, we do a variable analysis, and we determine the values that are assigned to each variable. And in all of these steps, we had to make abstractions and assumptions to be able to implement this. And for instance, one of the abstractions that we made is to assume that variables defined in any context can be used in any other context. And finally, we were able to generate the call graph. During our analysis, we ran into some complicated dynamic code structures that cannot be handled by static analysis. And one example of that is the code that you see on the right, where the developers decided to query the database to determine which function they need to call. And in a case like that, you cannot rely on static analysis to determine the target functions. So what we do here is that we provide a plugin API for analysts, which is written in Go, and we call these plugins custom static analysis, and we provided them for the applications in our data set. And this is essentially a callback into the call graph generation code that can help our static analysis to determine the potential targets for these function calls. And this is an example of what this code would look like. We then evaluated our tool on 4 popular web applications: WordPress, Joomla, Drupal, and phpMyAdmin, and we mapped 45 CVEs to the source code of these applications. And then once we debloated them, we looked at the reduction in terms of lines of code, and we observed 18% reduction for applications debloated by Minimalist. We also observed 38% removal of vulnerabilities. And then we also went ahead and performed automated tests on these applications. We ran a crawler and a monkey testing framework on top of it, and on the same entry points, and we didn't observe any breakage, meaning that we didn't remove any code that wasn't supposed to be removed. And we also compared this to state-of-the-art, which was the dynamic debloating of less is more, where for the same usage profiles, we would see 53% reduction in terms of size, 73% removal of CVEs, but during our automated tests, we observed multiple cases where dynamic debloating was too strict and removed the functionality, whereas from those same entry points, users could invoke them and therefore trigger a broken functionality in the applications. So to conclude, we presented Minimalist, which is a static analysis tool that can analyze PHP applications and generate their call graph. We then integrated this information with the web server logs and the entry points, and we were able to prune this call graph to debloat unused files and functions in PHP applications. And the main takeaway here is that we were able to show that it is possible to statically debloat applications without incurring the high performance overhead, and the debloated applications can also maintain their usability. We have open sourced our artifacts. We received shiny badges from USENIX, and you can go to debloating.com to look at the code. So with that, I would conclude this talk, and I'm happy to take your questions.
Thanks, speaker.